To interpret the effect that a categorical explanatory variable has on the response variable in a logistic regression model, we use odds ratios. To see how this is done, let's go back to our example where we had a 4-level categorical explanatory variable represented in the model such as this. To represent this 4-level categorical explanatory variable, we had 3 separate indicator variables where A was the base level. A common mistake that people make when they try to interpret these odds ratios is to use the exponential function with, let's say, one of these betas, let's say beta 1, and then they interpret then, this does end up being an odds ratio, then they interpret it the following way. The odds of a success are exponential function evaluated at beta 1 times as large for level B than for all of the other levels, where this is the actual mistake. Rather, the correct interpretation for the exponential function evaluated at beta 1 is this. The odds of a success are the exponential function evaluated at beta 1 times as large for level B than for level A. The reason being is because, remember, A was the base level. To further see this, let's take a look at how we would form an odds ratio. Again, basic principles, an odds ratio is a ratio of 2 separate odds of a success. So in this particular case, the odds of a success for, let's say, level B would be where I have x1 equal 1, x2 equals 0, x3 is equal to 0. And I would get then the exponential function evaluated at beta 0 plus beta 1. Then for A, the odds of success for level A, all these indicator variables are equal to 0. So I would have then just simply the exponential function evaluated at beta 0. Look what happens. The beta 0's cancel, and this is where I get my exponential function evaluated at beta 1. Now, one can make similar interpretations for the exponential function evaluated at beta 2. You're comparing C to A. The exponential function evaluated at beta 3 will be comparing level D to A. Now you might be wondering, well, what happens if I don't want to compare to A? Maybe I want to compare, let's say, level B to level C. You could do that as well. Go back to the basic principles of what an odds ratio is. Let's find the odds of a success for level B, and we're going to divide it by the odds of a success for level C. When I do that, write out the corresponding odds in terms of the model, the beta 0's cancel out, and I'm left with the exponential function evaluated at beta 1 minus beta 2. So that's how that would be calculated. Then for level B to D, the exponential function evaluated at beta 1 minus beta 3, and also you could do level C to D as well. The key is, again, always go back to basic principles of the odds ratio being the ratio of 2 odds. Write out these 2 odds in terms of the model itself, do some simplification, and you get the odds ratio of interest. So with that then, you might be wondering, okay, well, what about inference? Yeah, you can do inferences with these as well. What about a walled confidence interval for the odds ratio comparing B to C? Now we can see, as in C as in SEE, we can see that this particular odds ratio is a little bit more complicated. So how would I find then the walled confidence interval for that? Well, similar to what we've done before, we first find the walled confidence interval for beta 1 minus beta 2. So what one would do is find the estimate beta hat 1 minus beta hat 2 plus or minus the value from the standard normal distribution, that quantile, times the square root then of the estimated variance of beta hat 1 minus beta hat 2. What is this estimated variance? Well, see, variance hat, estimated variance of beta hat 1, get that from the covariance matrix, plus the estimated variance of beta hat 2, plus 2 times the covariance of beta hat 1 and beta hat 2, the estimated covariance. Again, get those elements, get those items from the estimated covariance matrix. Okay. Okay, that would be, first of all, that's for the confidence interval for beta 1 minus beta 2. Now for the odds ratio, you use the exponential function with that. Sorry, I forgot to include that immediately. Okay. Now let's take a look at an example that goes back to the control the tomato spotted wilt virus. I want to now interpret the control variable. I want to interpret the infestation variable for this particular model, so I have a better understanding of what affects the probability or the odds of these plants becoming getting infected with the virus. Now, we've previously saw that the infest and control interaction term was important for our model. So we would want to only interpret then the model that has that interaction term in it. However, for teaching purposes, let's start with the model that does not have the interaction because it will be simpler to work with. Then we'll go to the model that does have the interaction. So we previously found that the model without the interaction looked like this. This is the estimated model, that is. So if I wanted to find then the corresponding odds ratios for control, this is what I can do. Let me come on over here to tin. So my results are stored in mod.fit, and I can pull out my coefficients. So we can see, for example, beta hat 2 is negative 0.79. Then, if I, let me actually go down to control here. So the third and the fourth elements of that vector gives me my beta hats that I want to work with because those correspond to control. So if I use the exponential function with that mod.fit $ coefficients, I get the estimated odds ratio comparing C to A and then N to A. If I want the odds ratio comparing C to N, what do? Well, actually, in my program I have N to C. So N would be in the numerator, C would be in the denominator. Well, I would take the beta hat 3 from my model, subtract off the beta hat 2 from my model, use the exponential function with that, and there's my corresponding odds ratio. Okay, let's come back over here. So again, in my model, sometimes it's helpful to write this out. Here's beta hat 0, here's beta hat 1, here's beta hat 2, here's beta hat 3. Now, because of how mod.fit $ coefficient works, the fourth element is beta hat 3. The third element is beta hat 2. So that's why I made that, that calculation. So, for example, the estimated odds ratio comparing level N to level B, see, this one right here, is the exponential function evaluated at 0.5152, or in other words, 1.67. So the estimated odds of plants showing symptoms are 1.67 times as large for using no control methods than for using a biological control, where the infestation method is held constant. Remember, I always had to add that extra part there for any additional explanatory variables. So this makes some intuitive sense in this particular case, that you would hope that if you're trying to control the virus transmission, that if you tried some kind of control like biological, it would be better than doing no control overall. You would hope that that would be the case. And it does, in this sample, it appears that it's true relative to this model. Now, because we are interested in the reduction of these plants coming down with the virus or showing symptoms, then it might be of interest in this particular case to actually invert the odds ratio rather than having it being a greater than 1. So if I inverted this odds ratio, I could say the estimated odds of plants showing symptoms are about 0.6 times as large for a biological control method than for no control method. Thus, biological, in that case, you have less symptoms than you would with no control. And one could go further and say, well, using the spider mites, this biological control is estimated to reduce the odds of a plant showing symptoms by about 40%. In this particular application, these interpretations might be more of interest than our previous one. Now, and perhaps I should have brought this up before. When we did the no control to the chemical control, here's the actual derivation of that corresponding odds ratio. That's why I did the exponential function of evaluated beta 3 minus beta 2, or the corresponding estimate exponential function evaluated beta hat 3 minus beta hat 2. Okay, so which method, B or C, reduces the estimated odds more, reduces the estimated odds of being infected? So let's go back up here. So this is my estimated odds ratio comparing C to B. So notice the odds of infection are less for C, since that's in my numerator, than it is for B. So which reduces the odds of infection more, which is estimated to? C is. So the chemical control in this particular sample is working better than the biological control. Of course, we need to still do inferences to the population, so this is only for the sample itself. Now, to do these inferences, we can then do confidence intervals. The confidence function, remember that's a generic function. There's a method function in the stats package that does profile likelihood ratio intervals. We've used it before to find profile likelihood ratio intervals for a regression parameter, a beta. The problem though with this function though is that it only works for one parameter at a time. But we have a situation where we might have two parameters that we need to work with. So because of that, we have one of two options of how we can get these profile, or any kind of actually confidence interval associated with the odds ratios of interest. The first one you could say is almost like a little bit of a trick, where what we could do is change the ordering of the levels for the variable of interest so that with a different base level, we will only have one parameter, one regression parameter that we need to work with. So for example, in this particular case, when I was comparing N to C, how about we just make maybe C as the base level, so that then my beta hats that I get out, I only need to look at one of those beta hats, the one corresponding to the N indicator variable, to get my estimated odds ratio, and then use confident to get the profile likelihood ratio interval. Try that on your own to make sure that you can do that. Now, a more general way to do this process, maybe better way, is to use the MC profile package or the EMmeans package. Let's talk about how we can do that here. So with the MC profile package, remember what we need to do is first find a coefficient matrix, or you could say a K matrix in my coding. This is the K matrix that we want corresponding to control to find all three estimated odds ratios and all three corresponding confidence intervals. So in this matrix, let's say I want to compare C to B. Notice how I have the columns nicely labeled. So eventually this will allow me to take the exponential function evaluated at beta 2 to find the confidence interval when I want to compare C to B. Let's go back up to our model. Remember, beta hat 2 is that coefficient on the C indicator variable. That's why I was using that. Next, the N versus B. This will allow me to eventually find the odds ratio corresponding to the exponential function evaluated at beta 3. Remember, beta hat 3 corresponded to the end indicator variable. And then to find then N to C, this is going to give me the exponential function evaluated at beta 3 minus beta 2. Why do I want that? Well, this comes back to right there. Okay. So again, this K matrix gives me my coefficients on the betas that I want in my corresponding confidence that I need eventually for my corresponding confidence interval. How do I form that matrix? Similar to what we've done before. I have a K gets matrix, and then I write out all those corresponding zeros and ones and one negative one. I write it out in a nice organized manner so that I have 3 rows, I have 4 columns, and of course I have to put by row equal true there so that when R enters these numbers into the matrix, it will enter this one into the first row, this one into the second row, and so on. Remember, the default for matrix is actually to enter in by column, and so that won't give us the correct matrix. Then I put some nice descriptive names associated with the rows and the columns that we see here. Next, I use the MC profile function in the MC profile package. This again evaluates -2 log lambda for a whole bunch of different beta values. Notice how I use CM to specify where K is. Here is my results from my model fit from using GLM. Then the confident function, or specifically the method function in MC profile corresponding to confident, takes all those -2 log lambdas, finds 95% confidence intervals for the 3 rows of that K matrix, and I'm not going to control the Familywise confidence level here. This gives me a confidence interval for the log odds ratio, or in other words, a confidence interval just for beta 2, a confidence interval just for beta 3, a confidence interval for beta 3 minus beta 2. So for example here, and then in the corresponding output, then here's my confidence interval for beta 3 minus beta 2, right there. Now, to find the confidence interval for the odds ratio, then this is where I apply the exponential function once again. Because of how the MC profile package is nicely set up, what I can do is actually just say exp of ci.log.or. This finds my corresponding odds ratio. So here is 2.8 is less than OR is less than 4.9. This is the OR comparing N to C. Okay. Now, if you wanted to invert then the corresponding odds ratio, one way to do it, odds ratios I should say, one way to do that is to take 1 divided by then the corresponding elements that are actually stored in ci.log.or. We've seen this kind of stuff before. A little bit of a trick to do this too is if you were to, instead of put a K there, put a -1 there, and it will work too. I'm sorry, instead of putting a K there, you put a -K there. Excuse me. So for example here, the 95% profile likelihood ratio confidence interval comparing N to B is 1.3 to 2.17. That's what we see right there. Notice also I failed to mention those are the estimates that we've actually had before when we calculated it a different way. So to interpret in this particular interval, I would say with 95% confidence, the odds of plants showing symptoms are between 1.3 and 2.17 times as large for using no control methods than for using a biological control, holding the infestation method constant. Notice 1 is not inside that interval. So what this is actually telling me is that indeed, if you don't use a control at all, these plants are going to come down with this virus more often than if you were to use, in this case, a biological control. Another way that you could phrase this interpretation then is with 95% confidence, the odds of plants showing symptoms are between 0.46 and 0.77 times as large for using a biological control versus no control. So I inverted the odds ratio, and some people might even prefer this. We can see that the biological control reduces the odds of infection by between 23 to 54% with 95% confidence and holding infestation method constant. Okay. How can we do this now in EMmeans? What we can do is, first of all, use the EMmeans functions, what we've done before. I put in my model fit. And then for specs, I only put in control. I do not put infest. The reason being is because we're only interested in control here. Infest has no effect on that corresponding odds ratio because we don't have the interaction in there. Then I need to say type equal response. Next, what I can do, and I've done this before, where first we need to use the contrast function. What this produces, some hypothesis tests using wall tests for the corresponding betas, or in this case, it will allow us to actually do the linear combinations that we want as well. I could do that control function outside of conf_int, but rather just simply to say space, I immediately put that into the object of conf_int. I do not want any family-wise confidence interval control. I want 95% intervals. Here's what we get. If I want to compare B to C, I get an estimated odds ratio of 2.2. Here's my corresponding confidence interval, 1.7 to about 2.9. Note that I did not need an at argument in there for control. The reason being is because control is a factor. There's a fixed number of levels, and so what the EMmeans package will do, and the corresponding function will do, is say, okay, let's look at all possible combinations of those levels. Now, if one wanted to, let's say, invert the corresponding odds ratios, what one could do is use reverse pairwise as method. I guess I should have mentioned this before. Notice method equal pairwise right there. That allowed me to do B versus C, B versus N, C versus N. To invert these odds ratios, I can use REV for reverse and then do pairwise. Okay. Some comments here. So in the specs argument, again, we only put control. We did not put infest. The reason, again, was because infest does not have an effect on the corresponding odds ratios for control because I didn't have that interaction. And so this leads then to something maybe I should have mentioned earlier. Why is the EMmeans package called EMmeans? Well, the E stands for estimated, the M stands for marginal, and then we have means. So essentially what we're doing here is that we're finding a marginal mean here, or the marginal effect of control where we don't have to worry about infest. That's where this name comes from. Talked about the at argument already before. I talked about using contrast in conf_int, talked about pairwise and reverse pairwise. Again, we prefer to do profile likelihood ratio intervals, but as you can see here, the walled intervals are very similar to the profile likelihood ratio intervals because I have such a large sample size. Remember, I have 100 plants per greenhouse, and I have quite a few greenhouses. One should also look at the odds ratios for the infest variable too. Please see my corresponding calculations in the program. Now, what happens if we did include the interaction? So in other words, now we have this extra part of the model. This unfortunately makes things more complicated, as we've seen before with dealing with interactions. So we're going to focus on two different cases here corresponding to this interaction to help you see what's going on. I'm even going to include some color coding here too to help you see the corresponding parts of the output. Let's say I want to compare the odds ratio comparing levels N to B with infest2 equals 0. I have to specify what infest2 is because notice we have the interaction. It is going to have an effect on the response, even if I'm only interpreting control. So my odds ratio then for level N of control will be found like this. I take the odds of a success, or odds of infection in this case, where C is equal to 0, N is equal to 1, meaning I only have the N level. Infest2 is equal to 0. Then the corresponding estimated odds ratio is exp raised to the exp evaluated beta 0 plus beta 3. To help you see these indices here, let me put in what the beta hats are in this model. Okay, so notice what happens when C is equal to 0. So that means this is going to disappear, this is going to disappear, and then look what happens when infest2 is equal to 0. Notice that this is going to disappear as well. And also, sorry, that will disappear too. So notice I have beta hat 0 and I have beta hat 3 left. So in terms of the population odds ratio, that's where I get the exponential function value evaluated at beta 0 plus beta 3. Then, when I compare to the case for level B, when I have level B, the C control indicator variable is 0, the N indicator variable is 0 as well. So notice this disappears and I'm only left with that part right there. And so that's why I get the exponential function evaluated at beta 3. Let me do a little bit of erasing here. Okay. Now, what if infest2 is equal to 1? How does that affect things? Now, I have the N is equal to 1, infest2 is equal to 1. So look what happens now to my numerator for my odds ratio. I can remove the C, wherever you see a C. But now control N is 1, infest2 is 1, so now I have to worry about beta 5. I have to worry about beta 1 as well. I have to worry about beta 3 and beta 0. So now I have this as my population version of that odds ratio. When I look at level B of the control variable, C and N are zeros in terms of their indicator variables. So now this disappears, this disappears, this disappears, and what am I left with? Actually, no, excuse me, that does not disappear. There we go. Infest2 is equal to 1, that's why it doesn't disappear. And so now I have beta 0 plus beta 1 in terms of the population odds ratio. So then when I simplify, I'm left with the exponential function evaluated at beta 3 plus beta 5. Okay. For the other odds ratios, find those on your own. You can look at some of my code here to help see what the correct answers should be. Okay. So in the end, I'm going to have 6 different odds ratios that I need to examine because there are 2 levels of control, 2 levels of infest, 3 levels of control. So once again, let's take a look at how we can do this in the MC profile package. We're going to first look at N versus B with infest2 equals 0. Remember, that only involves beta 3. So when I form my K matrix, I only need to worry about beta 3 as having a non-zero value. But when I do N versus B with infest2 equal 1, now I have beta 3 and beta 5. So look what happens. I have a 1 here for beta 3. I have a 1 here for beta 5. Again, take a look at C versus B and N versus C on your own. So I put all these zeros, ones, and negative ones into my K matrix. I have some nice labels here so that one can make better sense of what's going on. I then use my MC profile function with the resulting model fit from the interaction model. Here's my coefficient matrix. A whole bunch of negative 2 log lambda values are going to be generated and put into linear dot combo. Then conf itself is going to take those to find the intervals that we need. Since I put linear dot combo there, level 0.95, I'm not going to make any family-wise confidence level adjustments. Then I can use the exp function with those corresponding confidence intervals for the log odds ratios, and this is what I get. So my confidence interval for n versus b when infest2 is equal to 0 is 2.1 to 4.5. When infest2 though is 1, notice how that really changes. 0.671 to 1.375. Here are my corresponding estimated odds ratios as well, quite different. Why does this occur? Because we have the interaction in the model. Remember the basic definition of interaction. How one explanatory variable affects the response is dependent upon the level of another explanatory variable. We see how this occurs here. How the control affects the response is dependent upon the infestation method. That's why when we did a hypothesis test for that interaction, we came up with a small p-value indicating there was sufficient evidence that the interaction was important. One could also use the walled function inside of MC profile to find the corresponding walled intervals. The reason why I did this here is so that we can make a direct comparison to what we get for EMmeans shortly. Okay, so some examples here. The estimated odds ratio comparing level N to level B with infest2 equal 1 is equal to exp of evaluated at beta hat 3 plus beta hat 5. If you go back to the estimated model, here's beta hat 3, here's beta hat 5, and I get 0.96. So what this says then is that if infest2, if I use a second infestation method, the type of control is not having much of an effect of preventing spread of the virus. Kind of weird to think about that, but it's not working very well. Now, if I were to find the corresponding confidence interval for that same scenario, notice what I get here, 0.67 to 1.38. We already saw that. This is using then the profile likelihood ratio intervals. So with 95% confidence, the odds of plants showing symptoms are between 0.67 and 1.38 times as large for no control than for a biological control when infected thrips are released in the greenhouse. Notice that 1 is inside that interval. So that means there isn't sufficient evidence to say that there's really a difference between these two control methods. So, in other words, the biological method isn't working. Now, though, when I compare N to B with infestation method equal 0, though, we saw we got a odds ratio confidence interval which did not contain 1. So we can see in this particular case that because this is greater than 1, N means no control, and that's in the numerator. What that is saying is that doing nothing at all increases the odds, increases the probability of these plants becoming infected when compared to a biological control. So in other words, the biological control is reducing the odds of infection in this particular case. So, some comments. Many more interpretations are possible, and to fully interpret then these variables in the model, you would need to look at the other combinations of these variables as well. One could also look at the Familywise error rate and control that. In my program, I show how to do that, for example, like with a Bonferroni method. Let's now take a look at how we can do this all with EMmeans. I'm going to put the results from EMmeans into an object called calc.s.inter for interaction. And the code is very similar to what we have before. My object is the results from GLM when I use the interaction. My specs argument is equal to tilde infest plus control. So first of all, notice I have both variables there, because when I interpret control, I know I have that interaction, so I need to specify the particular level of infest. That's why it's there. Now you might be wondering, well, why don't I see something like this? Infest control in there, because after all, we do have an interaction in our model. That's not needed. This is the difference with this specs argument from a formula argument in GLM. All you are doing here in the specs argument is specifying the particular variables of interest. Maybe it's a little bit unfortunate that the authors of this package made this syntax so similar to a formula argument, because you can see how one can mistaken how to use it. But in the end, this is what you have to get used to, and that's why there are some quirks with using EMmeans. Then I specify type equal response. Next, I use my confident function, where inside there I put the results from the contrast function. Notice this is where I put in the results from EMmeans. Method equal, I'm going to first work with, or in this particular case, I'm just going to work with the reverse pairwise combination. So rather than saying B in the numerator, C in the denominator, I'm going to put C in the numerator, B in the denominator. You know, sometimes you just have to do both to see which ones you would prefer to use. Then for my simple argument inside a contrast, what I want to specify is that I only want to look at odds ratios corresponding to control. And so what this package then recognizes that, okay, you want odds ratios corresponding to control, but I'm going to show you what happens for all the levels of infest. Okay? No family-wise confidence level adjustment. I'm going to find 95% walled intervals. So, for example, if I want to compare N to B when infest is equal to 1, notice what I get, 2.1 to 4.5, which is very, very similar to what we saw before with a profile likelihood ratio interval. Why are they similar? It's because we have a large sample size. Okay. So, the results from using the MC profile package with walled match with what we have there, so that's good. And I've already talked about this second comment there. Okay, so what this section of my notes does, it allows us to see how we can use odds ratios to interpret the effect that a categorical explanatory variable has on a response in a logistic regression model. Both the MC profile package and the EMmeans package are very useful in this situation to allow you to look at all the different odds ratios that one needs for a full interpretation.